Good afternoon, everyone. My name is Hamda Al-Hosseini and I am a researcher at the UAE Research Program for Rain Enhancement Science. It's my pleasure to welcome you all to the 15th session of the UAE Rain Enhancement Hub webinar series. Today's session is titled Numerical Simulation of Aerosol Effects on Rain Enhancement Seeding Results. This session focuses on the use of numerical simulation to assess the impacts of aerosols on cloud precipitation processes and the effectiveness of rain enhancement. In particular, the presentation examines the role of cloud condensation nuclei and ice nuclei in aerosols, and how variations in aerosol conditions can affect cloud microphysics and precipitation outcomes. It will also highlight how high-resolution cloud and precipitation modeling can support a better scientific understanding of rain seeding strategies under different atmospheric and aerosol conditions. We are honored to have with us today Professor Zhaofeng Liu, Grade 2 researcher at the Weather Modification Center of the China Meteorological Administration and leading meteorological talent at the China Meteorological Administration affiliated with Peking University of China. Professor Liu received her PhD from Peking University of China and has extensive expertise in cloud and precipitation physics. Her research focuses on the development of cloud precipitation and cloud seeding numerical models, as well as laboratory and field experiments related to weather modification. She has served as principal investigator for a national key research and development program and for a project funded by the National Natural Science Foundation of China. Her work has made significant contributions to advancing the scientific understanding of aerosol cloud precipitation interactions and their implications for rain enhancement. Before we begin, a quick reminder that you will have the opportunity to ask questions during the Q&A session at the end of the presentation. Please feel free to type the questions in the chat box and we will address them all. With that, I'm pleased to hand it over to Professor Zhaofeng Liu, and the floor is yours. Professor Liu will join us in a few minutes. Just wait for her.
Is it time to start? Okay. Good afternoon, UAE friends we are also the weather modification colleagues. And it's my pleasure. Can you hear me? It's okay. So I start my presentation. Okay. It's my great pleasure to have the opportunity to introduce my research work on the aerosol effects on weather modification. And I want to introduce my research work through the following 6 parts. And first, I want to introduce the microprocessors and the seeding mechanisms, and to introduce research objectives, and briefly introduce the seeding models used in this research. And the fourth part, I will introduce 4 seeding cases. And the last one is to introduce laboratory research and a few experiments in China. In mixed phased cloud, there are warm cloud processes and cold cloud processes. Warm cloud processes, these are the liquid jobs, such as cloud water, rainwater, and the cold cloud processes is mixed phase cloud water substances. And the warm rain processes, because the falling speed is related to the size of the liquid drops. Those different falling speed makes the different size droplets encountering and collision. So making the larger droplets even larger. And this is known as the gravitational cousins, which is the most important process for cloud drop growth in one cloud. That is the one cloud collision and cousin process. The chase with 2 different sizes of drops and contact the capture and form the big drops. Another important process is the breakup. Also, through this process also will generate lots of the rain drops. And for the cold cloud process is a Boltzmann process, because the central vapor pressure of ice is lower than the over liquid water, so supercold droplets will evaporate, and water vapor deposits onto the ice crystals. So it causes them to grow rapidly. And the Boltzmann process is the most important for the mixed cloud, for the cold cloud processes. And the weather modification, especially seeding for rain enhancement, we introduce the CCN or artificial IN into clouds to change the rain growth process. And for the cold rain mechanism, use artificial ice nuclei through the Boltzmann process to accelerate the growth of snow graupel or rain, these precipitation particles. And for warm rain mechanism, introduce the CCN to accelerate the cousin and to accelerate the rain formation and the growth. So the glaciogenic seeding with the coolant or silver iodide, and the ice nuclei is under the minus 38 degrees Celsius, it will be homogeneous nucleation process. But for the higher temperature, it will be the heterogeneous nucleation. It should be helped by the ice nuclei. And these are the ice nuclei, natural ice nuclei, including the mineral dust, soot particles, biological particles, and all these some organic material effective IN. And this is the kanji, listed all the natural IN. We can see that the natural IN is not very high, the nucleation efficiency, and also the temperature should be a lower temperature to be nucleated. So the silver iodide is the most widely used seeding agent because of its the high nucleation temperature and high nucleation efficiency. The ice water surface energy is 4 to 5 times smaller than the ice vapor surface energy. So the critical radius for emulsion, freezing, nucleation can be 4 to 5 times smaller than for the deposition nucleation. These are the deposition nucleation and the freezing nucleation. And also the nucleation process is affected by many factors, such as atmospheric temperature, humidity conditions, and the particle size, and the composition of the seeding agent. And also, it will be related to the particle generation method of the seeding agent, such as the burning of solution and the burning of flares or explosive breakup of silver iodide. Silver iodide also will be affected by the number of cloud droplets, because connector freezing and emulsion freezing, it will be related to the number of concentration of cloud droplets. For the higher, for 5,000 per cc, after 30 minutes, all silver iodide particles nucleated. But for the cleaner, for 50 drops per cc, after 100 minutes, only 20% of silver iodide nucleated. And the silver iodide also related to the relative humidity, and also related to the size. For example, for emulsion mode, the 20 nanometer is low as minus 35 degrees Celsius, only 20% nucleated. But for the 10 times larger particle at minus 10 degrees Celsius, 40% nucleated in 3 seconds. And the hygroscopic seeding is based on the hypothesis that the hygroscopic seeding accelerates precipitation formation by suppressing the activation of natural, less hygroscopic particles, such as the large CCN, and by promoting the formation of the larger water droplet directly use GCCN or ultra GCCN. Hygroscopic flare seeding includes some materials, such as this is the structure of the pyrotechnic flares. It including the hygroscopic materials and solidary materials, and some combustion materials. And this is the composition of South Africa flare with the different size. We can see that the small particles and the large particles, the chemical components are similar after the combustion of the flare. And the next second, I want to introduce the research objects. High CCN concentration tend to generate more cloud droplets and decrease cloud droplet size and narrow the droplet spectrum. So with the decreased cloud droplet size, it will also affect the warm-ring Coulson processes. For the diameter of cloud, the 10 micrometers, the collation rate is only 10%. But for the 30 micrometer, the collation rate is 80%. So it will affect the mixed phase precipitation process also, such as the Raman process. And this is airborne observation in China, the marine type of CCN and the continental CCN. So the high graphical seeding is to add more competitive CCN, such as the large CCN, GCCN, or larger CCN, to clouds along with the natural CCN to affect the development of clouds and the precipitation. So the natural CCN affects the seeding effects of cloud seeding. And for the fixed phase cloud, the artificial ice nuclei is added into the cloud to compensate for the insufficiency of natural ice nuclei, such as a coolant or silver iodide. So compared with CCN effects, the IN effects are much more complicated and far from well understood due to the varied activation properties and the different ice nuclei measurement method. This is observed the measured data by my colleague You Laiguan in 1963 and 1995. We can see this is a value at the 3 temperatures ice nuclei. The IN concentration increased from 1963 to 1995, 15 times, extremely high during the pollution conditions. And sand dust, this line is the sand dust. During sand dust events, the concentration of IN increased significantly. So the glaciogenic seeding is to add a seeding agent to generate artificial IN to clouds, along with the natural IN to affect the development of clouds and the precipitation. So the natural ice nuclei affects the effects of cloud seeding. Aerosol can act as cloud CCN or IN. Both of them affect cloud microphysics through their role in nucleation cloud drops or ice particles. CCN concentration affects one cloud precipitation, and IN concentration affects cold cloud precipitation. So aerosol can affect the development of clouds and the precipitation, which in turn affects the effects of cloud seeding. And the next part, I want to introduce the seeding model. Cloud model and the seeding model is very important for the weather modification research. The advantage for the model is we can use the model to distinguish the seeding effect from natural cloud and do sensitivity test with 1 or 2 factors. And also the most important, we can repeat the simulation. So use the cloud model to do some research to help the development of weather modification, such as the hypothesis of the seeding of weather modification and assessment of the seedability, experimental design, operational decision, and the project elevation and understanding of the seeding effects. In China, in weather modification, we have weather modification center. We have been developed and using models to do weather modifications. In 1960s, as the first cloud model will be developed, and in 1987, 2-moment convective cloud models is developed, and 2002, 3-dimensional cloud series models that's named CAMS. At that time, Weather Modification Center of China belonged to the CAMS, the Chinese Academy of Meteorology Sciences. So we named our cloud scheme as CAMS. And later we added the Hill process to this to CAMS scheme. All these models are coupled with MM2, MM4, or MM5 And later in 2004, the cloud models are coupled with WRF. Our scheme is the water substances, including all water substances except Hill, and to preserve the positivity and the conservation and the stability of water substances, a quasi-implicit calculation framework was developed, because the water substances are always positive. The quasi-implicit calculation is to preserve the possibility, and a specific calculation sequences is used to calculate the cloud physical variables. And some microphysical processes is uniquely, such as the auto-conversion of cloud to rain drops. We use FC, the function broadness of the cloud droplet size function. So we don't need the threshold of the cloud water. And the isonucleation of ice with the related super saturation and the time change of temperature. And the freezing raindrops to grapple use freezing probability to function to calculate this process. And our model running twice daily, and these are the cloud band distribution, and this is the cold cloud water, and this is a cloud vertical structure of the model simulation. And we also developed the seeding models, such as the three-dimensional convector model. We developed a silver iodide seeding for 4 nucleation modes based on the DeMott 1995. It's the function of temperature and supersaturation, and also developed the NaCl salt powder to calculate the salt resolved droplet as a mass and the number concentration. And also based on the Wolfram's model, the silver iodide seeding code is coupled with the Wolf models. And now we are developing the Wolfram's the hygroscopic seeding models with the salt powder. And the next part, I want to introduce the simulation of aerosol on seeding effects. There are totally 4 cases. The first one is the influence of grapple density and the falling speed on cloud seeding. This is to the seeding is to mitigate the heavy rainfall with the silver iodide seeding. Because the density of grapple particles varies widely, and the falling speed of the grapple change accordingly. This is the empirical approximations derived from the observation of locator and hops, and most early models to use this relation observations to calculate this falling speed of the grapple, snow, and hill. And in our models, we use this also this observations result. And these are the King and the Melbourne's conference to use the falling speed of grapple and some other precipitational particles. There are low density, medium density, and high density grapples. And the physical processes affected by the falling speed and the density of grapple particles is the collision causal process. because the density will affect the area of the grapple, and the falling speed will affect the paths within a time step. And also the deposition and the melting processes, such as phase change process, is affected by the falling speed, because it will change the energy exchange. And also the auto-converting grapple to hill is affected by the density. So if we change the falling speed and the density of grapple, totally 8 microphysical processes, 7 processes have to be changed. Use this model to decrease precipitation for a heavy rainfall case in South China. We calculated the silver iodide of NAER, the silver iodide aerosol, and NAIM, the silver particle emulsion into the cloud drop. This is the sensitivity simulations result. This column is the total precipitation. We can see that with a high grapple density and the strong falling speed, there are more precipitations. It can be as big as 4.9 more precipitations. Due to the altered distribution of falling speed of grapple and the updraft, you can see the black one is the updraft velocity, and all these are the falling speed of grapple. So the larger falling speed of grapple can to surpass the uphold of the upper draft, to fall down to the surface and to form the precipitation. So the larger VG and higher density, more rainfall amount. And for the seeding with silver iodide, the size is set to 0.1 micrometer, and these are the seeding amount, the silver iodide particle per kilogram of air. And we can see that we seeded at the time point of 120 minutes. At this time, we started to seeding. After seeding, you can series of the seeding, different seeding amount. All these seeding simulation can decrease the precipitation, and the maximum grid point rainfall intensity also is decreased. For this red one is a seeding, and the black one is unseeded. And the microprocesses of the changed for the precipitation is during the seeding start at 120 minutes, lasted 30 minutes. During the seeding, the melting of grapple terrain is decreased. And later, after the seeding ended, the grapple grows gradually and fall to the warmer, to the warm zones and melt to the raindrops. And after the seeding ended, the evaporation, there are much more small raindrops. So the evaporation of raindrops is contributed to the precipitation reduce. And with after the seeding, we with the overseeded method to decrease the precipitation, we can see that for the control run, there can reduce the precipitation 25%. But with the higher grapple density and stronger falling speed, the seeding effect is reduced to 15%. It's also because the falling speed of this test and the relation with the updraft, wind updraft. After seeding, the precipitation efficiency are reduced for after seeding. So all these seeding tests, the precipitations are reduced. The second one, I want to introduce the aerosol on rain enhancement. We use the three-dimensional convective salt powder seeding model. It's used the three-dimensional convective salt model to do the seeding simulations. This slide is to introduce a natural unseeded convective process. This is happened in East China, my hometown. The summer precipitation process case. These are the rain source terms for unseeded. And the ACR, that's the red one, is the autoconversion of cloud to rain is small and occurs over a short time period. And during the the first 30 minutes, cloud water collects and cooled into rainwater, and the raindrops grows slowly. And the black one, and 30 minutes later, the emulsion, the green one, the melting of grapple to rain is dominated for the rain source terms. And seeding is calculated with the salt powder. We calculate the salt powder, salt resolved drops, the mass concentration and the number concentration, mass mixing and concentration and number concentration. We seeded at this area at one temperature areas and exist with the cloud water. And at the time developed, this is the seeding time, point experiment. You can see at 12 o'clock that at that time the raindrops started to appear. It can get much more rain enhancement. And this is the seeding amount sensitivity experiment. The seeding with higher than 10 per liquid, and the size of the salt powder is 15 micrometers. It can reach the rain enhancement. And the microprocesses of the salt resolved droplets is including the cousins with cloud water and ice crystals and grapple and rain drops. And these are the distribution of salt resolved drops. This is the vertical section and the horizontal section. From this one, we can see that this one is the zero line, and we can see that after seeding at this height, the salt resolved drops reach the negative temperature zones. So it will also affect the mixed phase process. Seeding with the seeding effects of aerosols of the control marine and polluted condition. We can see that this is a control, is the ordinary the background of aerosol. the precipitation increases after seeding slowly, and the red one is the marine condition. The marine after seeding precipitation shows a sustained slight decrease and resulting a rainfall separation effect. And the green one is the polluted CCN distribution. And the unseeded precipitation is significantly lower than that in the other two conditions, such as the control and the marine. And also the seed leads to a sharp increase in rainfalls, with a maximum enhancement of 70% compared to natural clouds. And after seeding, the precipitation efficiency changed after seeding, and for the polluted conditions, the precipitation efficiency enlarged greatly. So it also resulted to the rain enhancement. The third one, I want to introduce the snow enhancement and the different backgrounds to consider the CCN and the IN, use the Wolfram's, use the IN seeding. There is a snowfall case in Beijing, and a haze event. Originally, it's a haze event, and followed by the formation of rainfall and snowfall. So I choose this case to do the simulation with the severe, the clean air and ordinary condition and the polluted conditions. These are the observations, and this is precipitation simulation. The sensitivity test of test of cloud drop number and ice nuclear. The ice nuclear NC is set to different size, different value according to consider the CCN influence. That is the control is the base of the simulation, and this one is for the clean air, and this one is for the polluted air. And the keeping the ice nucleation process is based on fracture. The presentation didn't show the entire information of this slide. And the ice nucleation process, there are two coefficient values, such as NIN and BIN. According to the fracture in 1962, the BIN is 0.6, and Bordeaux in 1975 is 0.3, and by Yolai-Guan in 1963 is also, and in 1995 it's very similar to 0.3 for 2, and the NIN is different greatly. For fracture, it's the lowest value, and for Beijing we use the 6.53 or 100 for in 1960s and the 1990s. So we designed the sensitivity test with these values. The HIN 001 to stand for the fractures value, and HIN 100 to stand for the 1990s values, and to test the CCN and IN for the weather modifications effect. These are the averaged the total water substances of cloud water, ice crystals, number of ice crystals, ice crystal mass content, and the number concentration of snowfall, and the snow particles and the mass content of snow particles. With less CM, that is the red one, we can see that the QC was much less, but the CN had little effect of all these ice crystals and snow waters. And with more IN, that is HIN 100 for these two tests, more ice crystals were nucleated and more snow particles were generated. And use the IN, artificial IN for the seeding. This is the daily precipitation distribution change after seeding. The letter A, B, C, D, these are the 4 decreasing centers after seeding. And the E, F, G, the red and orange colors stand for the increasing centers. We can see that these two with the more IN ice nuclear, we can see that the more IN reduces the artificial seeding effect. That is, the seeding centers value is lower than the less IN test. And also reduce the reduction of the snowfall in the reduction center of the seeding. And with more IN, with more IN, the seeding effect was able to shift approximately 0.6% from the total is 3.9%, and with higher CCN and higher IN concentration, the seeding, the ring enhancement effect is reduced from 3.9% to 3.3%. And the last case is for the ring enhancement and a different aerosol background, that is CCN, with the Wolf NSSL experiment scheme with IN seeding. This is a model simulation. At 2014, the NCCL is the only cloud expressed scheme to calculate the CCN effect. So I choose this NSSL scheme to use simulation. But this is when to test the NSSL scheme, I run the last one, the snow case of Beijing. And after run the model's result, you can see that this is the liquid water of cloud water for the NSSL scheme. And all these are the other schemes results, such as the marine, WD, MU, M6, and others. And there's a liquid water content of the snowfall case. It's not correct, as it's not reasonable. So I check the model of the CSSL. We can see that the IN calculation is not correct for the NSSL. This is the Fletcher line, this is the Cooper line, and that one is the NSL original one. So it's 1,000 smaller or less than other schemes. So I changed the error and to plus the 1,000 times for the parameters of the NSSL, and after that, the model simulation is reasonable. So in this case, also it's indication that the ion really affects the cloud and the precipitation process. And we designed the seeding experiment with the CCN with 3 values, and 1050 for clean one, and 5000 for ordinary condition, and 8000 for pollution conditions. And the IN, the seeding agent number is 1000 and 10,000 and 100,000. These are the valuation of the precipitation with seeding and without seeding. This column is the different CCN number of the clean one, ordinary one, and the pollution one. And these 3 lines is the seeding amount for these 3 values. At this page, that we can increase precipitation is shown in shaded area, is increased precipitation area, and the blue contours is the rain reduction areas. We can see that the CCN and will affect the seeding effect. Increasing or decreasing the rainfall intensity is related to the amount of seeding ice and the CCN. And we can see the higher CCN, less increased precipitation, and the more decreased precipitations. So CCN really affects the IN seeding effect for rain enhancement. And this is the total rain enhancement valuations. We can see the seeding effect of the same amount of the artificial IN, that is the blue. The blue one, the same color, stand for the same seeding amount of IN. It's quite different with the CCN conditions. This one is the most amount of rain enhancement for the clean CCN conditions. And after seeding, the microphysical also was changed. The ice crystal mainly grows through the process of deposition, and the snow also mainly grows through deposition, and followed by the rainmaking processes. And the rainwater mainly comes from the melting of snow and gravel particles. This image showed the 3 microphysical processes of snow terms. We can see that the higher CCN, the deposition growth of snow is reduced, and the snow collected of crystal of ice crystal and the snow are also reduced, and the melting of snow and gravel to rainwater is also weakened, and because of the seed as the microphysicals of the snow and the gravel terms, so the seeding effect is changed with different CCN. And I want to also introduce the current work, the developing and simulation of hygroscopic seeding model with wolf model. Coupled the salt powder seeding model with wolf CAMS model. So this is a salt resolved number concentration distribution and the cloud water number concentration distribution. This is the mass content of the salt powder, and this is the precipitation. And the last one is the exchange of the precipitation after seeding. We can see that it's really slowly, and the rain enhancement can be in enhanced to 2 millimeters at a grid. And we also developing a super droplet beam seeding simulation with LES model, and with the superparticle method to calculate the transport and the nucleation process, and with the beam model to calculate the droplet's growth of one cloud. And this one is the control without seeding, and the blue one is the for rainwater. We can see that after seeding, the rainfall appears, and without seeding, there's no precipitation. And after the seeding experiment show that the radius of solar powder larger than 4 micrometer, the rainfall enhancement in all experiments can be reached. But for radius less than 3 micrometer, it's failed to increase the rainfall under heavy polluted ground conditions, and could even result in negative health rain enhancement. And the last one, I want to introduce the laboratory research and the field experiment. In China, we developed the mixing at the thermal cloud chamber and the portable small cloud chamber and the expansion cloud chamber with 70 cubic meters and 15 and 1 cubic meters expansion cloud chamber. With the 70 cubic meters cloud chamber to conduct the expansion experiment at an upward velocity of updraft velocity of 14 meter per second. As the aerosol number concentration increase, cloud droplet number concentration increase accordingly. This is the aerosol number concentration. This is the cloud water concentration. The cloud droplet formed in the expansion cloud chamber. And we also checked the 3 relatively commonly used for the high Groupus seeding field experiment with these 3 materials. In clean air and adequate water vapor, the seeding agent, and this is the pollution air in adequate water. The black one is the black line is the background, and the 3 others are the seeding agent. We can see the seeding agent with a small size. All this is the seeding agent is -0.1 micrometer. Fail to form cloud droplet size distribution favorable for raindrop growth. So the large hygroscopic particles should be selected as much as possible. For the high hygroscopic materials, will be stick together. So to measure the high hygroscopic seeding agent spectrum, we should use the wind tunnel to dilution the seeding agent number concentration. This last upper one is the wind tunnel built in last century, and use this one we measured the hygroscopic seeding flare used in China. And the below it is the sealed wind tunnel. We use this the seed tunnel to simulate the real condition of the seeding agent aerosol generated, such as we use aircraft or UAV craft to broadcast the seeding agent in in strong wind and in low temperature, and also at a low pressure to simulate the real environment of the seeding aerosol formation. So it can be in this wind tunnel, we can decrease the pressure to 300 Pascal and the temperature to as low as minus 40 degrees Celsius. And in this tunnel, we can burn the pyrotechnic flares in this tunnel to study the spectrum, hygroscopic particle spectrum, and the CCN nucleation, and also the glaciogenic particle spectrum. And okay, I have to change it to another slide. Okay, thank you. Okay, thank you. From the last one, okay. The wind tunnel we use to measure the aerosol particles online or offline. And the next part, I want to introduce a field experiment. In 1958 to 1970, China built started the cloud observation in Lushan Mountain in East China. At that mountain, there's half days in is foggy days or raining days. So it's a reasonable place to do the observation of cloud water and the seeding experiment. And at this cloud observation base, we got the first the observation data of cloud water, and some data also be used in our cloud models. And in 2015, continue the cloud observation to get a long-term data. So we started the observation again. And this is me. To lead a group for the rebuild of the platform and do the observation. In Lushan, also some precipitation phenomena, especially such as the hail, snow, frozen rain, and heavy storms. And from 2015 to 2024, 30 equipment as 18 kinds equipment type to be built in the Lushan observation base. We have built 6 observation sites. The 2 is at the foothill of the mountain, and another 2 at the slope of the mountain, and another as the last 2 site is at the top of the mountain. So we can catch the cloud and the precipitation process from the north of the mountain, and from the east of the mountain. We build the equipment from the aerosol measurement, and to measure the cloud drop and the rain drop spectrum. These are the images of the this observation site image. And with this equipment to measure the aerosol and the cloud and the rain drop, the seeding experiment is carried out during 2024 and during 2022, 23, 24, and 25. This is the seeding with ground-based generator. We can see that this is the time period of the seeding. We can see that after seeding, the size distribution of aerosol is increased. And this is the seeding with high hygroscopic powder near ground. With the micro rain radar, we can see the rain size near the close to the ground is increased. So with this document, this equipment, we can to test the seeding agent or the seeding method to their response of the aerosol and the cloud water and the rainwater. And also it's convenient to change the seeding distance and the seeding time and the seeding height. We also use a UAV to do the seeding of the generator. So to the conclusion and the last one. So I just made the solution of this and the discussion. And so the next time, in the future, we still have to do the seeding simulation with the more detailed seeding model, and to consider it as a effect of the IN and CCN background, and also do some field experiment and field and laboratory research along with the seeding model to develop the and also to develop the seeding agent and the seeding method. It's over 1 hour time. Thank you so much. I finished my presentation.
Thank you so much, Professor Jofeng Liu, for your valuable presentation on the numerical simulation of aerosol effects on rain enhancement seeding results. Your presentation have provided clear scientific insights into the aerosol cloud precipitation interactions and demonstrated how numerical modeling can strengthen our understanding of rain enhancement process under varying atmospheric conditions. Our audience, since we ran out of time, if you have any inquiries or would like additional information about Professor Liu's research, please feel free to contact us or visit the UAE RAP website. As a reminder, this webinar has been recorded and will be made available on our website for future references. Please stay tuned for our upcoming sessions of the Rain Enhancement Hub webinar series, where we will continue to share scientific advances and research developments in rainfall enhancement science and technology. Thank you all for joining us today and have a wonderful day ahead.